Hello and welcome to this third episode in the talks about how to pre-process diffusion data, i.e. how to correct for distortions and subject movement in diffusion data. If you remember the previous two talks, we are now coming to practicalities, and what I mean by practicalities is what do we need in order to run topup and EDDY to do all these things that we have looked at from a more theoretical perspective so far. And what I'm going to do is I'm going to take two examples. One is taken from EDDY-data, which is a little bit more complicated, and another one that might be a bit closer to the kind of data that you would collect on a day-to-day basis. So the first example is EDDY-data. What this data consists of is a large number of diffusion-weighted volumes and a smaller number of B0-weighted volumes that have been interspersed among the data. There are two repetitions of all the data, so they're acquired with phase encoding left-right and phase encoding right-left, i.e. with distortions in opposite direction. Now I should stress that it's not necessary to repeat the whole diffusion acquisition. It was something we did in the EDDY-data, because when we were making the decisions about how to acquire them, we didn't yet know how difficult it would be to correct for these distortions, and we thought that if we had both directions, then it would be easier for us. In retrospect, you could say that was probably overkill. We didn't really need it, but this is the data we have. And also, there's the same diffusion table for both repetitions, i.e. Each and every diffusion gradient has been acquired twice with the two different phase encode directions. Now, so if we look at this data, what we have is we have the B0s that are affected by susceptibility distortions, as we talked about earlier. We have all the diffusion weighted images that are affected by susceptibility distortions and eddy current distortions. And also note that the eddy current distortions are likely to be different for each and every one of these different diffusion gradients or different diffusion volumes. And of course, everything is affected by subject movement. So let us start by estimating the susceptibility induced field. And in order to do that, we start by extracting some B0 volumes using FSL ROI, and the sum over here, we're just taking two pairs. So we collect these two pairs into a single file using FSL merge. So you can see that we have two images, two B0s acquired with phase encoding going in right to left direction, and two with phase encoding going in left to right direction. And we call them something like my B0s in this case. I should stress that increasingly it turns out you don't actually need more than one pair of B0 volumes. By having more than one pair, so in this case we have two pairs, by having more than one pair, you pretty much just increase the execution time, and you don't really buy very much at all in terms of accuracy for the estimated field. Right. Then what we do, we need to inform topup about the acquisition parameters. So remember, when we looked at topup, in order to do the calculations there, we needed to know exactly how each and every one of the images in topup had been acquired. So what we need to, for each and every volume, tell them in which direction is the phase encode direction. So this is this 3-element initial vector here. The fact that you have a 1 in the first column means that phase encoding is in the x direction. The sign here tells you that it goes from right to left. And the fourth column here is the total readout time in seconds. So that is the time it takes to read out that entire slice in seconds. And we sort of fill this file up so that we have one line for each volume that you have in your image file. And we can call it, for example, acqparams.txt. One thing I should say already now is that you don't actually need to know the readout time. I mean, if you get the readout time wrong, so for example you put in 0.02 in all of these rows instead of 0.051, it is not going to change your results at all. The only thing that is going to change is the scaling of the off-resonance field that is calculated by topup. But because that scaling is then wrong as we then use it in EDDY as well, in terms of correcting these distortions, it's going to be exactly the same. So you don't necessarily need to know the readout time, except for some very, very few cases where, for example, if you have data that's been acquired with different readout times in the different directions, then you need to know that, but that would be very rare. So most of the time you don't actually need to worry about it. In addition to the image file and the acq-params.txt, you need to provide a configuration file. You always need to have a configuration file. This is the default configuration file, and that can be used whenever the matrix size of your image is such that in each direction it is an integer multiple of 2. If it isn't, you need to use one called b0 to b0_1 instead. It will give you exactly the same results. The only difference is that it will take a little bit longer to run. Then what you need to do is you need to specify where your output shall go. So you give a name, so in this case --out equals my topup, and this tells topup where to write the output. And the output is going to be written as 2 files. One is the name you have given, _movepar for movement parameters, .txt. And that is simply a file with motion parameters relative to the first volume. Because obviously, we have 4 volumes here. The subject might, well, ideally it shouldn't have moved, but the subject might have moved a little. And if we don't estimate the movement parameters at the same time as we're trying to estimate the field, any difference caused by movement would lead to a misestimation of the field, i.e. it would be sort of leak into the estimation of the field and we would get that wrong. So we're estimating these motion parameters as well. Another important thing to know is that the space of the field that is estimated is the space of the very first volume in the data file that you pass into topup. And that's the one volume where you have the zero movement parameters telling you that this is the reference space. The reason that this is important is because obviously if you're gonna have a field and you're gonna use that to undistort a set of images, you need to know that that field is aligned, is perfectly aligned, is perfectly registered to those images, because otherwise you're going to get it wrong. Now, the good thing about topup and EDDY is that if you make sure that the very first volume in your topup dataset is also the very first volume in your EDDY dataset, i.e. the data that you feed into EDDY, then this is ensured automatically. You will automatically be in the right space. But just keep an eye on that. Make sure that you know which volume you have put as the first volume into the data file of topup, and because that is the space in which the field will be estimated. Now, so as I said, my topup _movepar.txt, that is one of the outputs. The other outputs is called my_topup_field_coef, and what this is a set of, or is an image of spline coefficients that when convolved with cubic splines will give you the field. So this is not actually the field. It needs to be decoded by convolving it with splines in order to give you the field. But this is something that is done by EDDY when you feed it into there. So we have this. We now know the susceptibility induced field in the space of the first volume there. So back to the full data set, and what we now want to do is we want to correct the entire data set for eddy current distortions and subject movement, and obviously also apply what we have now found out about the susceptibility induced field. So the way to do that is that we first start by collecting all the data into a single file using FSL merge. So in this case, we had data in the left-right direction, in the right-left direction, and we just merge all of those, and we can call the resulting data file, for example, left-right_right-left. Then what we need to do is we need to make an index file, and that is simply a text file with one number, an index, for each and every volume in your data file. And what that text file does, it informs EDDY about how the individual volumes were acquired. So you see in 1, 1, 1, 1, 1, and essentially tells EDDY that all of these volumes that have the index 1 were acquired with these acquisition parameters. 2, 2, 2, 2, it tells that all of the images with the index 2 were acquired with these acquisition parameters that happen to be the same in this case, and then we have the 3s, etc. But in addition to referring into the acquisition parameters file, it also refers into the movement parameters file. So that means that we can use these already estimated movement parameters as a starting guess for the subject position for each volume. And again, this is something, so this seemed like a very good idea at the time. It probably is a very good idea, but as it turns out, EDDY is actually sufficiently robust that even if you don't supply this initial estimate, it will get the movement parameters right. So this thing is less critical than we initially thought it was. Now, as you know, EDDY uses a prediction maker, Soltar, and he needs to know the b-values and b-vals, i.e. the b-values, and the b-vectors, i.e. the diffusion gradient vectors, for each and every volume. So these needs to be put in as well. So we have the b-vals and the b-vecs, and remember that is to be the b-vals and the b-vecs for all of these volumes, both in the left-right and the right-left direction. And you also need to make a brain mask. So there's simply a binary mask that tells you which voxels are brain. You can use the same that you use for DTI fit or bedpost. That is probably the one you should use. But you should also know that this is really not very critical. If that brain mask isn't fantastic, it doesn't really matter, because all that EDDY needs it for is to know roughly where the brain is in order to pick a representative collection of voxels from which to estimate the hyperparameters for the Gaussian process. So again, it's not super critical. Now we have all of these things. We have the acquisition parameters, we have the output from topup, we have our index.txt file, we have the b-vals and b-vecs, we have the brain mask. So now we can finally put these together and run EDDY, the most horrible command line in all of FSL. So here's the data, and here comes the acquisition parameters, the index file, the b-vals and the b-vecs, the brain mask, the topup output, and then obviously we have to tell EDDY where to write the results. So that's how to run EDDY, and well, topup and EDDY on a data set of the HCP type. Now, a simpler and perhaps more realistic example for the kind of data sets that you use in practice when you're not using the HCP data would be that you have one diffusion data set consisting of n diffusion weighted volumes and small n B0 volumes. Now, the B0 volumes can be interspersed, they probably should, but keep 2 or 3 up front. So start out with 2 or 3 B0 volumes. In addition to that, acquire 2 or 3 B0 volumes with opposing phase encoding. And acquire, ideally at least, acquire those right before you acquire the diffusion data. And the reason for this is that you want these to be in as similar a space as possible, i.e. you want to minimize the risk of subject movement between acquiring these and acquiring these. And if you were to put these at the very end of your data set, that would mean that we present a much longer time between acquiring these B0s and the B0s with the opposing phase encode direction. And the reason that we are recommending acquiring 2 or 3 is not because 2 or 3 pairs are needed for top-up. As I said, you only really need 1 pair for that. It is simply to make sure that you get at least 1 B0 from each direction that isn't broken. And what I mean by broken is where you don't have the subject moving suddenly during the acquisition of that volume. Because if that has happened, you will see a sort of telltale zigzag pattern if you look at a coronal slice or a sagittal slice of that image, and it tells you you can't use it for estimating the susceptibility field. So acquire 2 or 3 in each direction, inspect them to see if they're good, and when you've done that, you pick 1 good B0 volume for each phase and code direction using FSL A. As before, collect them into 1 4D file using FSL merge, and if you look at this you can see, whoops, what I've done here is I've put the B0 file, which is the first volume of the diffusion dataset, as the first volume in the 4D file that I'm going to feed into topup. Because remember, this is the image or the volume that determine the space that we estimate the susceptibility field in. So it's important that that is the same one. Then we create the text file called acqparams.txt. It doesn't have to be called that, it's a good name. And again, remember, that is not crucial. It's not critical to get that right. If you don't know it, if you can't get it for your data, just put in some number. I tend to always put in 0.05 when in doubt. And then we run topup, and we're using the same command line as before. So once we've run topup, now we want to run EDDY. And index.txt is now very simple, because they're all acquired with the same acquisition parameters. So it's just a file of ones, as many ones as there are volumes in your diffusion weighted dataset. And also, as I said before, it's not really critical that you use these interspersed B0s to get a good first estimate of movement, because it's all taken care of internally by EDDY these days. So index.txt just once. And then we run EDDY in the same way as we did before. So EDDY, data file, acquisition parameters, index.txt just once. Your bvex, your bvals, create the brain mask in the same way as before, feed in the topup results so we know that the susceptibility field, and tell the output, or tell EDDY where to put the output. Right, so that's how to run EDDY from a practical perspective. So let's have a look at some results and what can it actually do. So this is one example. So this is some HCP data. It's a b-value of 3000, so it's a relatively high b-value. Blip up, blip down. Well, it's not actually, this is blip left, blip left, blip right. So on the left hand side you can see the data before any correction, and you can see that it's sort of moving around quite a lot, and this is due to eddy currents, the uncorrected eddy currents. And on the right you can see that it's much more stationary, much more still now. So b-value 3000, already quite a high b-value. The images look quite different, so it's already quite a difficult data set for traditional methods to deal with. The next example is even harder. So this is a b-value of 10,000. Now what we're having is phase encoding in the y direction, so it really is blip up, blip down. And if you look at on the left hand side, this is before any correction. If I were able to stop this video, which I'm not annoyingly, you would see that the individual images are completely different. They're really, there's no way you could tell they're even from the same brain just by looking at 2 individual images. And yet, if you look here on the right, you can see that it's done quite a good job of correcting the distortions. What I want to do now is I want to zoom in on this little sulcus down here. This is probably going to be hard to see, so you're probably going to have to sit back from the screen a little bit and squint. So on the left hand side you can see that little sulcus, And you can see through the different volumes, it's really jumping up and down, and it's not still at all. And trying to analyze this data under the assumption that for a given voxel, the different time points reflect the diffusion in that particular voxel would just be ridiculous. But if you look at the right-hand side, again, you probably have to sit back from the screen a little bit, squint with your eyes, and you can actually see that that's how, because it looks like it's writing really, really still. And as I said, this data set, p-value 10,000, is a really difficult data set, and yet you can see that it has done a very good job on controlling it, or of correcting it. Right. Then what I want to talk about is something called EDDY QC, which is a sort of quality control tool. So what EDDY does, so you remember you saw that you had to say --out and then give a name for the EDDY output. And the main EDDY output is going to be a file with that name and then called .nii.gz, and that is simply the corrected data. But EDDY will also output a lot of other files with the same name but with other extensions. And all of those are auxiliary information that tells you things about how, what parameters were estimated, what movements were estimated, what was the contrast to noise of the data, etc., etc. But that information could be more accessible, and that's where EDDY QC comes in. So EDDY QC is essentially a tool that takes those output files from EDDY and collate that information and present it in a format that is easily read by humans. And in addition to that, it has this really nice feature of, so what you have is the EDDY QC consists of two tools. It's the quad and the squad tools. And what you do with quad is you simply run quad once per subject in a directory where you have EDDY output. And what is going to be produced there is a .json file and a .pdf file per subject. Now the .pdf file is something you can read straight away, but what you can also do is that when you've done this for all subjects, you can then feed the .json files into a second level squad, and what that's going to do, it is going to collate that information across all the subjects in your study. It's going to produce a group quality control PDF that you can read, but in addition to that, it is also going to recalculate all the individual .json and .pdf files, such that you now know what is the quality of each and every subject's data set in relation to the average quality or overall quality of the data in your study. So let's just have a look at this. So this is an example of a biobank subject A. And here we have all the volumes, you have all the motion parameters, the between volume motion parameters, you have the within volume motion parameters, you have counts of outliers, etc. And what you can see here is that these are all green. And the reason they're all green is that first these parameters were collated from the EDDY output. Then, when that had been done on all the subjects, the average motion, the average translations, the average rotations, the average within volume motion, outliers, etc. were calculated. And then this subject was revisited with that information, which allowed us to put that subject in the context of all the other subjects. So we can see that absolute motion is actually smaller than average for this subject, the relative motion slightly higher, translations, etc. So you can see that these are all now within the context of the group as a whole, and because it sort of falls within that closely to the average of the group as a whole, so these are all labeled green, saying that okay, this is a good subject. On the right, we have another subject. Again, all the parameters were calculated for this subject. Then it was sort of revisited within the context of the average, and you can see that the absolute motion is much higher for this subject than typical. The relative motion is much higher for this subject than the typical. Translations higher, rotations higher. So all in all, this is a bad subject, and this is then being reflected by this subject being labeled red in all these different categories. Another thing that EDDY QC can do, it can take all your data and visualize key metrics from your data. So in this case is the contrast to noise ratio, in this case is the signal to noise ratio, and sort of visualize these metrics against a categorical or parametrical variable. So in this case you can look at the contrast to noise ratio for males versus females, which can be important. For example, if you want to do a group comparison between males and females, you don't want any differences to be due just to the fact that maybe you have poorer contrast to noise ratio in one group than in the other. And the same if you want to look at some diffusion parameter as a function of age, you don't want that to be driven completely by the signal to noise ratio, for example, being different in the older subjects compared to the younger subjects. And this is just to illustrate some aspect of the data quality. So probably the one measure you get out of EDDY QC that best capture the quality of the data is CNRI, contrast to noise ratio. And what we can see here is we can see how this correlates, or how this agrees with the subjective appearance of these images. So we have here 1, 2, 3 subjects, good subjects, so-so subject, and a bad subject. And if we look at the contrast to noise ratio, we can see that the good subject for all the different shells, so we have the B400 shell, the B1000 shell, and the B2600 shell. For all these shells, that subject is among the top subjects in this entire population. The so-so okay subject is sort of average on all these parameters, on the contrast noise ratio for all the shells. And the bad subjects, you can just looking at these images, you can see that, well, this doesn't look as good as the others. You can see that he is at the bottom for all of these parameters. So this was EDDY QC quality control, and this ends sort of the plain vanilla EDDY and distortion correction and motion correction talk. I mean, there is another talk where I go into more advanced EDDY features. It is not really necessarily part of the course. It's not going to, you don't need to listen to it to do the practical, for example. But if you happen to have a particular interest in distortion correction, motion correction, all of those things in diffusion data, it probably means you're a little bit geeky, but so am I. So if you're interested in that, please tune in to the EDDY Advanced Features talk, which will be the next talk in the series.